Okay, so Chapter 4, Podcast 2. Okay, talk about precipitation reactions. Hopefully you remember these as being double replacement. Okay, and this happens when you have ions in solution. Okay, and you add another solution that has ions in solution. And when those ions come together from the two different solutions, if it makes a insoluble ionic compound, you are going to see not a predictable, that's just silly, a precipitate. Okay. So, precipitation reactions. Yeah, okay. Sorry, I'm distracted, but I'll get back on board. Ready? Precipitation reaction. Let's look at a little video. Hang on while I swap things around. And we'll watch this little video.
The first precipitate will be produced from aqueous silver nitrate and aqueous sodium chloride.
Take a moment here and make sure that you can predict what is going to be the insoluble precipitate.
Aqueous sodium chloride is added to the silver nitrate solution. We observe a white precipitate of silver chloride. This heavy precipitate thickens and falls to the bottom of the test tube as more aqueous sodium chloride is added to the silver nitrate solution. This is a white precipitate of silver chloride. Again, we take aqueous silver nitrate. This time we are going to add aqueous sodium iodide. When the sodium iodide is added to the silver nitrate, we get a pale yellow precipitate of silver iodide. Note that this precipitate is not the same color as white silver chloride. It is very pale yellow or cream-colored. The cream silver iodide falls to the bottom of the tube and begins to form thick lumps.
Okay, so what we should do, or you should do, is make a page or something somewhere in a notebook where you can find it easily and call it colors, because we just learned the colors of two compounds. Silver chloride is white, silver iodide is a pale yellow. And we'll try to pick up on those when we, as we go along in class. Now, metathesis or exchange reactions. Okay, it's from a Greek word that means to transpose. And what we have to keep in mind is, why do these reactions occur? Why do they form something? Okay, and it's precisely that they do form something that there is a reaction. Bear with me while I get my pointer working. Okay, it's not just I don't know why I did that. Oops. Yeah, my pen's. Top tip. Now it should write. Okay, so the idea is that there's a driving force because we are going to make something. Okay, and we just saw the first thing that we would make is a precipitate. So if I add two ionic solutions, or solutions of ionic compounds, together, if those ionic compounds, any combination of the ions in those solutions, once I add them together, if they make an insoluble compound, I'm going to have a reaction, I'm going to make a precipitate. The other thing that we look for these things to make is a gas. Another thing, oh wait, sorry. If I combine them and they make a non-electrolyte, okay, or read that as a molecular compound. I think I just went off the screen, but molecular compound, then there will be a driving force for the reaction. The reaction will happen. The other thing is if I make a weak electrolyte. Okay, and what we're looking for is that the products are somewhat different than the reactants. All right, so let's take a moment. We're going to look at how we write different types of reactions. All right, I've got silver nitrate and potassium chloride, both aqueous solutions. If I do the classic double replacement, ions exchange with each other. Still remember that you have to have the cation with the anion, positive with negative, so it would make silver chloride. You know from your memorization solubility rules that will be a precipitate, and my other component in the solution would be potassium nitrate, and we know that to be soluble. Now sometimes you have to keep in mind, what is it exactly that I have in that compound? Do I have free ions floating around? Have I made a precipitate? Have I made a liquid? Have I made a gas? That's one of the reasons why I require you to put the states of matter. For the most part, you should know what the states of matter are when we write reactions. Okay, and you got to look for clues. Okay, so first thing we write is what we've done before in honors chem. Is molecular equation. You're given silver nitrate, potassium chloride in solutions. Switch partners, come up with silver chloride, the solid, and potassium nitrate soluble, so that's in solution. But that doesn't really tell us what's going on in the solution. Okay, so what we want to look at really is an ionic equation. And this gives us a whole big picture of exactly what is going on in that solution. What did each of my reactants look like before those solutions were mixed, and what did they look like after they were mixed? Okay, so in the ionic equation, all the strong electrolytes, strong acids, strong bases, soluble ionic salts, all of those are dissociated into their ions. So if we're working with the same equation, on the reactant side we're going to see a mix of silver plus ion, nitrate ion, the potassium ion, and the chloride ion. By the way, you should remember that silver is always a +1, and as a side note, zinc is always +2. Okay, so when we mix those, we know we form the solid, so that's going to be shown as together because it's going to form that crystalline structure. It is going to be together. And then I have remaining in solution potassium and the nitrate. Now be careful, because if you're talking about a limiting reactant problem, you may have some free silver and some free chloride ion, one or the other, okay, depending on what was limiting in the equation. That does not show up in your ionic equation. Okay, the excess reactant does not show up in your equation. That's just going to be part of the stoichiometry problem that you have to do. Okay. So again, this more accurately reflects exactly what's going on in that reaction mixture. A lot of times, we don't really care about the things not involved in the reaction, so we're going to cross those out. So for the net ionic equation, we want to see only those things that are reacting during the course of the reaction. So for the equation we started with, if the precipitate I make is silver chloride, the only reactants that show up in the net ionic are the silver ion and the chloride ion. Those things that didn't change, that were crossed out, those are called spectator ions, because all they're doing is looking. So, in review, writing a net ionic equation. First, write the balanced molecular equation. Determine whether you have a precipitate, determine whether you've made water, which would be a molecular compound, determine whether you made a weak electrolyte, perhaps something like acetic acid or hydrofluoric acid. Then you're going to dissociate all of the strong electrolytes. Okay, implied in that statement is not dissociating the weak electrolytes. Weak electrolytes are typically written together. Okay, for instance, hydrofluoric HF would be written as HF. Then you're going to cross out anything that remains unchanged, meaning the spectators, and then you're going to rewrite the net ionic equation with the species that are involved in the reaction with their states of matter. Okay, let's talk about acids. Okay. Acids are defined simply as substances that increase the concentration of hydrogen when they are dissolved in water. Okay, and the difference between acids and soluble ionic compounds are that acids ionize. Soluble ionic compounds dissociate. So, to figure out where I am, yes. So let's look at this quick, I'll get it quick for you in just a second, hang on. Center that in my page. Let's look at this little video, what's going on when I have a strong acid. Okay. The hydrochloric acid reacts with water, liquid. Hydrochloric is in the gas form, so we actually refer to it as hydrogen chloride. Reacting with water, bubbling through water, I'm going to create the chloride ion and the hydronium ion, which is the H3O+. Okay, hydronium ion. My pen doesn't work when I do that. All right, but the hydronium ion. Okay, so let's see what happens if I've got a bunch of hydrochloric molecules bubbling through water. Okay, if you notice, all of the hydrochloric molecules, hydrogen chloride molecules, have ionized, meaning the H plus from the hydrochloric has bonded, and that's the difference between ionization and dissociation, is the hydrogen plus has bonded with the water molecule to make H3O+. For all acids that contribute an H, you're going to see the hydronium ion. That's how it exists in water. We get lazy sometimes, just write H+. It really exists as H3O+, the hydronium. For simplicity's sake, sometimes we just use the H+. Okay. So that's a strong acid, 100% ionization. Hopefully you already moved ahead and answered that question. Now let's look at HF. HF reacting with water to form a fluoride ion, and again the hydronium ion. Okay. And then it actually goes back to the HF molecule and water. Okay.
You guys did? Sorry?
Okay. If you look here, see that symbol, that equilibrium symbol, means I have some of reactants present and I have some of those products present. And if you look at this solution, I have one fluoride ion, one hydronium ion, and the rest of it is the HF molecule and just plain water molecules. And this is what weak acids do. Weak acids only partially ionize. So primarily I'm going to have the HF molecule and water. I'm going to have a little bit of the fluoride ion and the hydronium ion. And that's the difference between a strong and a weak acid. Okay. Let's go through this. I don't know why I went back. Alright, so an Arrhenius definition of an acid is anything that increases the concentration of the H plus or the hydronium in reality when dissolved in water. Bronsted-Lowry defined them as proton donors. There are 7 that you need to memorize. Okay. Hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, chloric, and perchloric. You should also know the other 2 chloric acids, meaning the chlorous acid and hypochlorous acid. Bases. Arrhenius define bases as substances that increase the concentration of hydroxide when dissolved in water. Bronsted-Lowry defined them as proton acceptors. Okay. Strong bases, soluble metal salts of the alkali metals, calcium, strontium, and barium. Acid-base reactions, also known as neutralizations. Okay. The acid is going to donate a proton to the base. Okay, in this case, I have water actually acting as the acid, donating a hydrogen, H+, to the ammonia molecule. NH3 is ammonia. After they react, I have a hydroxide ion, and I have the ammonium ion. Generally, neutralization reactions occur, acid and base yielding salt and water. Those are general. Okay, so I have something like acetic acid reacting with sodium hydroxide, producing sodium acetate. Why that's written backwards, probably organic chemists write it that way. I would write it the other, but okay. And of course, water. Can you answer me why the acetic acid is drawn all together? I'm hoping you can, but I'm not going to answer that. You should know. Okay. Strong acid reacts with a strong base. The net ionic equation is H plus the hydroxide, both in solution, yielding water. What drives the reaction? The production of water, a molecular compound. Gas-forming reactions. These are some that you just need to know. Okay. When calcium carbonate reacts with hydrochloric acid, you would initially I would hope at least, can I have a pen? Write the products as CaCl2 in solution plus H2CO3 in solution. You need to know that H2CO3 readily decomposes to give carbon dioxide gas and water. One of those things you just need to know. I'm not going to say it again. Okay, so when a carbonate or a bicarbonate reacts with an acid, you're going to get a salt, carbon dioxide, and water. Similarly, you get a sulfite. Sulfite is an SO3. When that reacts with an acid, you're going to get a salt, sulfur dioxide, and water. Okay, because initially we would have written this as the strontium iodide plus H2SO3 in solution. That looks very similar to H2CO3, and it is. It does pretty much the same thing. Okay. If I have a sulfide reacting with an acid, okay, I'm going to get the hydrogen sulfide gas, and the reason why you would be very unpopular is because it smells like rotten eggs. Okay? So because we're forming that gas, that's a reason why this reaction would happen. Oxidation reduction is where we're going to pick up on the next podcast. Have a great day.